All right, reaction number 10. So this is going to be syn dihydroxylation. We're still adding two alcohols onto alkenes, but the stereochemistry is syn. Look right here. All right. There are two ways to do that. One of them use potassium permanganate in a basic solution and keep the temperatures cold, so low temperature. Potassium permanganate is commonly used for this reaction because it's inexpensive. It's potassium permanganate, the manganese is a strong oxidizing agent, but the only downside of this reaction is it give you a low yield, so you don't get a lot of product, right? Compared to an osmium tetroxide and NMO. NMO is down here, and methyl morpholine N oxide. What does it do? I'll show you what does it do or what it does later. But osmium tetroxide is even a better oxidizing agent, right? Give you a better yield, but it's more expensive. We use NMO to regenerate fresh osmium tetroxide during the reaction. I'll show you in a bit. The only downside of osmium tetroxide, besides expensive, is it's highly toxic. So you gotta watch out how the way that we use in the reaction. Okay, so there are two ways to do it. Just in case, if you look at other textbook or maybe look up on the internet, you might see the NMO here. It's replaced by just other reagent, but they're all the same thing. If you see osmium tetroxide, that's a syn dihydroxylation. Okay? All right, here's the mechanism. Now, you don't have to memorize the mechanism for this one, but only thing that you have to be able to explain is why we get this stereochemistry, syn dihydroxylation. Why this two OH group goes syn, okay, not anti. All right, so the first thing that happened is osmium tetroxide will interact with the alkene. If you still remember the platinum and interact with an alkene, it's considered reaction like that. This is similar to that, the same trend. So 3 plus 2, which means 3 atoms here and 2 atoms here. It goes 3 plus 2 cycloaddition. That's what they call it. That's the name of it, right? And osmium get on alkene on one side, both sides. Same side, I mean. Okay, so this is going to be similar to the hydrogenation. Same thing that platinum can approach alkene on the same side or one side at a time, bottom phase or top phase. Same thing with osmium. Osmium do the same thing. This one is at the top, right? And then water will attack on osmium, open the ring, proton transfer. So this hydronium ion donate proton to this oxide. So we get that. So we get OH there, right? And then osmium comes out, and you get an oxide right there, which can be protonated by that OH plus right there, and then you get the product, syn diol. Right? Now, NMO comes into play right here. Osmium with the oxidation number of 5 plus 1, 6. This is 6. Osmium plus 6, right? It's not usable for this reaction, and osmium is really expensive. So we want to recycle it, and that NMO come to play right here. So NMO will recycle this osmium 6 to osmium 8, and you get this guy get back to the next catalytic cycle. So in this case, we don't need to use a lot of osmium. Okay, but osmium is really, really expensive. All right. Now, if I ask you who control the stereochemistry, make a syn addition product, right there, this guy, osmium. So I guess on alkene on one side, they can do only one side. They can't be like one oxygen on top, the other oxygen from the bottom. It got to be on one side, right? Their arm is not as long. So now potassium permanganate, exactly the same mechanism. I'm not going to go over it, but who control the stereochemistry? Why the product is syn dihydroxylation? They go syn because of manganese right there. Gets on alkene on one side. See that? That's the only reason. Okay. All right. Predict the products here. So potassium permanganate in basic solutions, cold temperature. So this one going to be the syn dihydroxylation. So watch out for the stereochemistry. All right. So manganese can approach from the top phase. So you get that. Can go from the bottom as well. You get the other one. It's enantiomers. All right. Now osmium tetroxide do exactly the same thing. Right. In NMO, that's a recycle. Osmium tetroxide. Osmium can come from the top. You get one isomer. So OH, both OH on a wedge line. That wedge line. And osmium tetroxide can come from the bottom. You get OHs on the dashed line. All right. Down here, MCPPA, this metachloroperoxybenzoic acid. This is a peroxide will form an epoxide ring right there. All right, and then we open the ring, burst out the ring with the acid. So we protonate that oxygen will become protonated, become reactive. Water attack on the more substitute carbon. Right, you get that one, and the other one, this one, peroxy acid approach from the bottom, so you get bottom epoxide on dash, and then water will attack from the top face. Here we go. You get that. All right. So we have trans diols here. This is cis diols. Okay. All right. Let's summarize. Pretty much, we have learned most of the reactions so far. We got, I think, 2 more to go. Let's summarize this real quick on the next video.